last year, but in fact, we just saw a talk which covered the same material. So I can now say that this talk is in some way a footnote or a commentary on the previous talk. So it's very nice to. I want to say that if FIFA needs a consultant, I think there's a job waiting for you. So, I forgot to put my microphone on. I'm sorry. Yep. What's that? So in a sense, I'm, get to talk about what a three group is in this lecture, since we've already had a talk on two groups, but a much better place to start is to remind some of you and tell others what the two groupoid of Poisson brackets is. So what I want to do is, in some sense, say that the last talk was sort of about the way the equivalence classes of elements in this three group, which are a group, some sort of cohomology group, act on the equivalence classes of objects in this two groupoid. In other words, the Poisson brackets up to isomorphism. And so I can only approach this at the moment in a formal sense. I'm going to do it just through studying the formal neighborhoods of an object here. So if I forget to say that, just always sprinkle everything I say with the word formal. And the link is everything is going to be obtained by studying L-infinity algebras. So I'm kind of pleased with this work, even though it hasn't led anywhere yet, because it gives the first example that I've ever actually seen, having spent the last decade or more working, actually 15 years working on L-infinity algebras. I finally have an example, which is geometric, and you'll see this, I hope. So what's a two-groupoid? So I'm going to give two different definitions. So the first definition, I'm going to stick to the strict case. Although when I write two-groupoid, I'm thinking what some people would call a weak two-groupoid or a bi-groupoid. But since they're the right notion, I'm going to reserve the simpler term two-groupoid for those, and if you like, more complicated terms for the less useful notion of strict two-groupoids. But in fact, the Poisson two-groupoid is a strict two-groupoid. So I can start by describing what a strict two-groupoid is. It's a groupoid which, instead of having morphism sets, it has morphism groupoids. So it's a groupoid in groupoids. Now, so it sounds, I'm not just doing this because I want to categorify idly. I'm doing it because actually when you study two groupoids, you're really forced to. I hope I can convey that in the next few minutes. So here's the example. First, formally, those will be the objects. So we'll take all the Poisson brackets on a manifold as our objects, and then if I have a pair of Poisson brackets, then my one morphisms are the objects of the groupoid of morphisms. So I'm going to have, I'll call it script D for Deligne. So this is the Deligne morphism groupoid of from P to Q of the Deligne 2 groupoid and the objects here, which are the one morphisms, these are just diffeomorphisms which take P to Q. And the morphisms of the groupoid here, which are the two morphisms of the two groupoid, so now comes the point where it becomes apparent that I'm thinking formally. Those are the Hamiltonian diffeomorphisms. Because you see, a Hamiltonian diffeomorphism doesn't move us. It leaves us at P, and so any two diffeomorphisms that differ by a Hamiltonian diffeomorphism are to be thought of as equivalent morphisms. Yeah?
I'm getting ahead of you if I ask whether you mean the Hamiltonians of the Hamiltonian.
Yes. Well, formally, since I'm close to I'm thinking very formally, so I'm identifying them. I'm thinking of the diffeomorphism group as a pronilpotent group.
They're always the Casimir functions that you can throw into the Hamiltonian.
Oh, sorry. Yes, absolutely. Yes. So I mean the Hamiltonians. Yes, exactly. Oh, yes. That's the whole point. Yeah. Yeah. So the Hamiltonians. So Hamiltonian diffeomorphisms, HPF, where H sub F is the, or rather exp of this, where F is some function which we think of as being close to 0. And this is the vector field for the Poisson bracket P associated to F, and then this gives some diffeomorphism. So that's the sort of idea. Actually, if you wanted to turn this into a global object, one way to do it, so maybe it's better that dpq is the holonomy groupoid. So here you have a foliation of the diffeomorphism group of the manifold by Hamiltonian. Oh dear, yeah. So now I hit I hadn't thought this through. Okay, I take it back. Yeah. Okay. So why do I go to all this trouble? Because we want this construction, which, yeah? You should think of them, I mean, they act on one side. Yeah, so I forget which side. There's some complicated formula, and which was given in my 2000 paper. And there's earlier work of Deligne, who considers instead an analogous problem studying deformations of associative algebras. In fact, the formulas he gives are identical to the formulas I give, even though the contexts are different. And indeed, the one story is carried over into the other by Kontsevic's formality theorem. So there are some explicit formulas, but I want to get right away from explicit formulas immediately because you'll drown in explicit formulas. So there's a different point of view on this, which is, I think, much more powerful, which is to go to a simplicial point of view. The thing is that, recall that that if we have a groupoid, then we can obtain from it a simplicial set called its nerve, which actually completely captures the groupoid. It's a sort of Yoneda embedding. What we're doing is embedding groupoids in sheaves of sets on certain on a sub. Well, actually, there's we take the simplices and think of them as as small categories, and then so groupoids G go to simplicial sets. So we have the nerve of G, and the n simplices of this nerve are functors from n to G, and n here is this small category. So that's one point of view. So it's a sequence of objects with morphisms between them. And we can completely reconstruct the groupoid from this simplicial set. We can characterize which simplicial sets are nerves of groupoids, and functors between groupoids are simply simplicial maps of the associated simplicial set. So we get a full, faithful embedding of groupoids into simplicial sets, and it's even better than that because simplicial sets form a simplicial category, and that simplicial enrichment completely captures the enrichment of the category of groupoids over groupoids. Because, as you know, the morphisms between groupoids actually form a groupoid, not just a set. They're a natural transformation, natural equivalences. I'm sorry. What I mean is the isomorphisms of groupoids form a group. No, what am I saying? No, I said it right. Yeah. So this gives a full, faithful embedding of groupoids, the category of groupoids, into simplicial sets. So full means that any simplicial map between nerves is actually coming from a functor between groupoids. So there's no real reason. So the reason I like this is what it means is once you know the theory of simplicial sets, you can define groupoids without writing a page of axioms. All you need to do is state what is the condition on a simplicial set for it to be the nerve of a groupoid. And that's easy. I'm about to state it. Okay? So here it is. So suppose I'll introduce certain simplicial sets. These are called the horns. They sit inside the n simplex. It's just the union of all the faces of the simplex which contain the ith vertex. So I goes from 0 to n, and this is the union of all faces that meet the ith vertex. Okay? So if you've read the first chapter of any book on simplicial sets, you've met this guy because it comes up in the definition of Kahn fibrations or Kahn complexes, that's probably the most important concept in the theory of simplicial sets. So here's a little extract of that discussion. If I take the nerve and I look at, so now I take all simplicial maps from the n simplex to the nerve, and I'll interpret what this is in a moment, but for now let's just notice that it's the n simplices of the nerve. So I've already told you what they are. Well, by restriction to this subcomplex, I get a map of sets to the horns in the nerve. Okay? And the Kahn condition says these maps are surjective. And the condition for us to have a nerve of a groupoid is that these maps are bijections. So that's for n greater than 1. Okay? And it's really fabulous to see that that is true. You've got for example, at the level of n equals 2, we have these 3 different horns, and what we're saying is that we can fill in the missing interior and face inside the nerve in a unique way. So in this case, it becomes the existence and uniqueness of a composition, and here it becomes something like that, but with inverse built in. And then at the level n equals 3, it gives you associativity, and that inverse of inverse is inverse. And above n equals 3, it gives you no new information. So it's a very conceptual and efficient packaging of what a groupoid is, and now it becomes very easy to fix this. For higher groupoids, I'll just define, although I should really say X is the nerve. Oh, I misstated it. What I meant is G is a groupoid if, but now I'm just going to throw that away and identify a groupoid with its nerve, because it can be reconstructed from the nerve in a completely obvious way. And instead, I'll just tell you which simplicial sets are higher groupoids. So X is a K groupoid if these maps are bijections for n greater than K. That's all. And this seems like it doesn't stand a chance of working, but it's the charm of the subject is somehow that it works just fine. And it's definitely weaker than usual notions of higher groupoids, but weaker, I think, in just the right way. So, this, I still need this condition. Yeah, that I'm assuming in the background. Yeah. And, yeah, and then a morphism of K groupoids, a pseudo-functor in the suitable weakest sense, I simply mean a map of simplicial sets. So this is just by imitating this point of view on groupoids. So I think this point of view, well, I should give some references. For groupoids, I guess this is due to Grothendieck and Siegel. And for higher groupoids, it's due to Duskin. I should say Duskin and Glenn. And it's really very geometric. I've made it seem just some abstract homotopy theory idea, but what I should have said really is that the n simplices in the nerve of a groupoid are in some sense flat connections governed by the groupoid. See, the simplex is a very combinatorial thing, and so we put one object at each vertex. We put a morphism of the groupoid along each edge. We want a flatness condition. So over each 2 simplex, we require that the monodromy be trivial, and there are no higher conditions. And so you should think of higher groupoids as being captured by these simplicial sets, what we're in some sense saying is the simplices here are the flat connections on the combinatorial simplex governed by this higher groupoid. And if you perform this trick with this two-groupoid I introduced here, you get something which now I'm going to show you comes from L-infinity algebras. So that's the key idea of the talk. This is a, yeah. One higher. So as I said, for a groupoid, the only interesting cases were NS 2 and 3. So for a K groupoid, up to K plus 2. That's the K plus 1 gives you the data, and K plus 2 gives you the data such as it is, and K plus 2 gives you the associativity conditions. So for example, for a two-groupoid, you can reconstruct from it, the nerve itself of a two-groupoid is a notion that evolved independently of this. And I think it was not noticed by the people who wrote down what the nerve of a two-groupoid is, or even the nerve of a bigroupoid is. It wasn't noticed that it is pretty much characterized by this condition. But you can't completely reconstruct a bigroupoid from its nerve. You can reconstruct the composition at the highest level. So the two morphisms, you can reconstruct the composition, but the one morphisms, it just gives you a set of possible compositions. Because for n equals 2 in a two-groupoid, this is only surjective. It's not a bijection. So you can, if you've got some situation you want to work out a composition, you choose any lift whatsoever, that will give you some notion of composition. Now, by the axiom of choice, we can find such lifts for every possible composable pair of arrows. But we're not going to have strict associativity, and when you follow things through, you'll see that you can reconstruct the associator, and it'll have to satisfy a pentagon equation. So you do get a bigroupoid by throwing the axiom of choice at this data. But so moving beyond this talk, I think this is a better notion, because if you want to do sheaves of K groupoids, the descent theory for these guys is much more readable. Yeah?
Is there any reasonable way in which you can sort of recover having a section by saying it's a relation?
I don't know. And then the next question is measurable section, or continuous section, or differentiable section. Yeah.
Sections which are relations.
Yeah. So there is something in that. You've run the danger of recovering strict. So the question is, are you going to use the same relation for all I simultaneously? And that's been studied in Wales. And if you look at my paper, recent paper in Annals on this subject, I've got some comments in that direction, which may not answer your question, but there is a little bit you can say. Yeah. Can you speak up? Yeah.
Maybe some answers his question that in of a case equals 2, you can view the set of two simplices as giving composition of one simplicity as a hyperrelation.
Oh, hyperrelation. Yeah.
And then it surjectively, and then it maps to the third phase.
Okay. Okay. Moving along. Yeah. So, no, it's okay. Yeah. So let's go back to sorry. Let's go back to the original nerve of a groupoid, or actually, let's just think about the nerve of a group for a little bit. So as you know, one way to get groups, one of the first methods that was developed, is to construct them from Lie algebras, and in particular from nilpotent Lie algebras. So suppose G is a nilpotent Lie algebra. So there's an obvious way to construct a simplicial set. Namely, so simplicial set, And let me call this mysteriously MC of G. So this is Mora Carton. And actually, following Kahn, one often uses the word space for simplicial set, because from his point of view, topological spaces are simply simplicial sets. So you could call this the Moret-Cartan space of the Lie algebra. This is the same thing, actually. I mean, I've changed notation here from Hinich, but Hinich has written a lot about this construction, and he calls it the nerve of the Lie algebra. And in some sense, this construction is due to Sullivan. It's a special case of a much more general construction of Sullivan, and hence it sort of wasn't noticed, because it's such a special case. So what we do is we take connection forms on the n-simplex with values in G. So we're going to take a trivial... if we had the Lie group, we would have the notion of a principal bundle for that Lie group, and we're going to look at the trivial principal bundle. And we're then going to look at connection 1 forms on that principal bundle. Right? So now I'll change notation. For the simplex, I'll do delta superscript n. That will mean the actual physical simplex, the convex hull of n plus 1, the n plus 1 unit vectors in Rn plus 1. So, whereas the delta n I had before was a simplicial set. They're actually different, completely different objects. So I have this one form, a connection 1 form, and I want it to be flat to satisfy the Moret-Cartan equation. Okay? So this forms a simplicial set. For example, the face maps are just, if you restrict a connection to a face, and it was flat on the whole simplex, it'll be flat on that face, because this is a 2 form, and 2 forms restrict. So we have a simplicial set, and this simplicial set is not the nerve of a groupoid. So I found a way to locate inside here a simplicial subset, which is the nerve of a groupoid. It's actually the nerve of the Lie group associated to G by the Campbell-Hausdorff formula. And the way I do it is by putting a linear gauge condition on these simplices, on these connection forms. So it's a combinatorial analog of gauge theory. We have here, as you can imagine, a very large gauge flexibility here, which is what is preventing this from being the nerve of a groupoid. Yeah. Degeneracies also work. The degeneracies are, for example, if you take, well, if I take a 2-simplex and map the first few vertices to one end of a 1-simplex and the rest to the other end, that gives me an affine map. And now I pull back a connection 1 form, the pullback of a flat connection is flat. So all simplicial maps are sort of automatic. So let's impose a gauge condition. I'll be very mysterious here, but there's a sequence of operators on the differential forms on the n-simplex which reduce degree by 1 and which satisfy, they actually form a simplicial they're compatible with the simplicial maps. So, for example, if I restrict to a face of this simplex, then the corresponding operator S 1 degree down. So let's. Suppose I take the ith face, and now I have S 1 n down, and then this diagram commutes. So this is just an illustration. Actually, this analogous thing happens for any simplicial map between simplices, including degeneracies. And so this operator S satisfies a very, very interesting, it's given by an explicit formula. It gets more and more complicated as n increases, and it is if you like, related to the proof of the Poincare lemma. The Poincare lemma says that the de Rham cohomology of a simplex is trivial. And it comes about by picking a point and rescaling around it. So you could, for example, pick a vertex. Now, if you do that, then for any face which meets that vertex, you'll get a formula like this. But for the opposite face, you'll have a disaster. And what DuPont found was a way to improve the proof of the Poincare lemma in such a way that this continues to hold. So it's like a more modern approach to the de Rham theorem. And I don't know how he thought of it, but perhaps he did it by staring at We's proof of de Rham's theorem very long. Because, you know, We's proof is completely explicit. He tells you how precisely to find the exact forms which will interpolate between your closed differential form and one which you've constructed from a cocycle corresponding to it in cohomology. So, however, you can't possibly hope that this is a homotopy between the de Rham complex of the simplex and just the constants. That isn't compatible with this. Instead, it contracts you down to a little subcomplex which is isomorphic to the simplicial cochains of the simplex. So this is projection to the Whitney's elementary differential forms. So I don't have time to go into this in detail, but let's look at the one simplex. So P projects to the span of 1, T, and dt. And you see that this subcomplex in fact has the correct cohomology, and it's isomorphic to, in a completely explicit way, to the cochains, the simplicial cochains. How? Well, these functions, we can evaluate them on the zero simplices in the one simplex, and that gives us the map from these functions to zero cochains. So evaluate at the endpoints. And dt, we can integrate it, and that'll give us a one cochain. So that's a quick discussion of de Rham's theorem. And now, so I call this thing gamma. in imitation of the notation of who? I forget. I think Kahn calls it his construction capital gamma. That's the abelian case. So that would be if the Lie algebra was abelian, in which case what we're going to recover is the Eilenberg-MacLane space. So I just put a gauge condition S omega equals 0. There. So that's my gauge theory in a kind of algebraic setting. Now I can prove a theorem that this simplicial set is isomorphic to the nerve of the Lie group associated to G. Okay? And now I can take this definition and simply replace everywhere a Lie algebra by an L-infinity algebra, and I'm going to get a notion of a n-groupoid associated to an L-infinity algebra. So I don't have time to explore all the ramifications of that, but I'll state what's going on. Somebody mentioned this is the one conference where you don't have to define a Poisson structure. This is almost the one conference where you don't have to define an L-infinity structure, but I think you do. So we have now G is a graded vector space. And we're going to have a differential on it, delta. I might have liked to call it little d, but that gets confusing because I'm going to have the de Rham differential as well. So I have to distinguish the differential here from the de Rham differential. And I could stop here. If I had no further non-zero structures, I would have an abelian L-infinity algebra. So an abelian L-infinity algebra is a complex of vector spaces. All right? So we're generalizing complexes of vector spaces. And now we have a bracket. So this goes from G tensor G to G. Actually, it goes from Gi tensor Gj to Gi plus j. And it's graded antisymmetric. So what that means is it's antisymmetric, except if x and y both happen to have odd degree, in which case it's symmetric. And in particular, if x equals y and x has degree 1, then it's a quadratic form. Okay? A quadratic form on G1 with values in G2. So now you're expecting me to say that this satisfies the Jacobi rule. And if it does, then we have a differential graded Lie algebra. Well, no, I first have an axiom, which is that d of xy equals dx y plus minus 1 to the I x dy. So this Leibniz rule holds just like it does in a differential graded Lie algebra. But the Jacobi rule only holds up to a correction involving a 3 bracket. So in order to continue, I need to introduce a 3 bracket, and this goes from GI1, tensor GI2, tensor GI3 to GI1 plus I2 plus I3 minus 1. And I'm just going to sort of say in words what's going on. This is graded antisymmetric in all 3 variables. So let me jot that down. And its differential gives the correction the right-hand side of the Jacobi rule. So its differential is the Jacobiator. Okay? So, and so on. So I'm not going to give you much more detail, but I will at least say that we potentially have brackets of all degrees so this goes from GI1 tensor up to GIK to GI1 plus up to IK plus 2 minus K. All right? And just as a parenthetic remark, if K is 1, you could say, well, this is an operator that goes from GI to GI plus 1. And it actually makes a lot of sense to identify the K equals 1 bracket with the differential. And then all the formulas become very, very delightful and uniform. And another remark I should make is that you can define what you mean by a nilpotent L-infinity algebra. So there's going to be, but I won't go into that. And what else should I say? That in this language we can say what we mean by a Lie n algebra. I think these came up earlier in the conference. Is simply an L-infinity algebra with GI equal to 0 if I is positive or I is less than or equal to negative n. So it's a L-infinity algebra of length n. And for example, well, you can see that this works for n equals 1. A Lie 1 algebra is a Lie algebra. Okay? And a Lie 2 algebra, it has length 2, and other than that, it satisfies these axioms. No? No? That would be an L-infinity. Well, it depends what you want. Do you want the notion of Lie n algebra to be a homotopy notion or not? So when we move to rational homotopy theory, yeah, I don't. Do I want? In other words, is the Moré-Cartan space a groupoid, or is it simply a space that has the homotopy type of a groupoid? Now, I don't know. In my talk, I'm choosing to distinguish those two notions. So likewise, I distinguish between the two notions that you're comparing.
Excuse me.
Yeah.
Just all of your brackets are graded antisymmetric. Huh?
Yes.
Then usually one should put the word super
somewhere.
Graded. That's the word
It's
super.
not the same thing. There are graded Lie algebras which are not Lie superalgebras, like Canal algebras, for example.
That's a different notion of grading. Yeah. It's just, there are two different, But if you like, just go back over all those papers and replace every integer by 2 times that integer. Okay? And you'll fix that problem, compatible with this convention. Yeah?
Is there any version where the anti-symmetry also gets corrected?
Corrected.
Well, why have anti-symmetry on the nose? Why not have it up?
Oh, well, I mean, you're asking the wrong person. I don't know anything except what I've seen in Reutenberg's work. So I'm completely, that's relatively, I would have said that was virgin territory, except it's not completely, oh God, I didn't, anyway. It has been deflowered. Let me say it explicitly. Okay. Okay, so you have to change the definition a little, but not very much. So we have to take now forms which have total degree. So omega is going to be omega 0 plus omega 1 plus omega 2 plus up to omega n. And omega I is an I form with values in G1 minus I. Okay, so that's compatible with what we did before for Lie algebras. And we modify this to d omega plus delta omega plus half the bracket of omega with itself. Remember, that's a quadratic form with values in G2. And now we have a cubic form, 1/6 of omega, 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 and so on, equals 0. So this notion of Maury-Cartan element, I think I first saw in Koncevich's paper on deformation quantization, as it happens. And I have now a theorem. So I have a whole slew of theorems. One is that this notion is homotopy invariant. So if I have two nilpotent L-infinity algebras which have this and an L-infinity, a linear L-infinity morphism between them, which is an isomorphism on cohomology, it gives an equivalent, a homotopy equivalence of these simplicial sets. So that's the reason why I've introduced this whole gadget. And the second result, so homotopy invariance. And secondly, that if Gi equals 0 for I less than or equal to negative n, then this guy is an n groupoid. Okay? If in addition, Gi equals 0 for I greater than 0, then it's an n group. An n group is a n groupoid with a single vertex. Okay? And this is obvious once you follow through the definition. So if I throw this construction, now we finally get back to the previous talk. So let me take Gi equal to lambda I plus 1 of a manifold. So here, this is the sections over M of the I plus first exterior power of the tangent bundle. Then, as you all know, there's a Schouten bracket on this guy, making it into a graded Lie algebra. Let's tensor with so let's make it nilpotent, or pro-nilpotent, nilpotent in some formal sense, by tensoring with this algebra of power series that vanish to zeroth order. And now we're in business. So we can, for example, you could take different differentials on this. If there's a background Poisson bracket, you can take that differential on the Schouten algebra as your differential. Or if the background Poisson bracket is 0, you can just take this with vanishing differential. And then it's just a graded Lie algebra. Okay? And now let me throw this construction at it. And I get, so the point is that this is the two-groupoid that I introduced earlier in the talk. Okay. So now I want to introduce an L-infinity algebra which captures more of the information. So what I'll do is take now gi equal to lambda I plus 1 of m. Let me leave out the part that makes it nilpotent, because that's just a standard ploy which we're going to just assume is being done. And let me add to it the de Rham complex. Okay? And so the differential is the Poisson differential on lambda and the de Rham differential on omega. All right? How about the higher brackets? Now it gets interesting. So I want to say that the inspiration for this construction came from reading the thesis of a student at Northwestern, a student of Manin called Denis Borisov, who was working in Hochschild homology, Hochschild cohomology. And so it was more in a A-infinite setting, but if one transports his A-infinite ideas to L-infinity and takes a very simple example, you get this. Okay. So the brackets. So let me denote elements here by x, y, z, and so on, and elements here by alpha, beta, gamma, and so on. All right? So the bracket of x and y, that's just the Schouten bracket. And there's only one other kind of bracket that occurs. So this is actually, despite the notation, so it's a k plus 1 bracket. You can antisymmetrize it yourself. All that says is that if the differential form occurs in some other index, you have to whiz it over all the way to the left using graded antisymmetry in order to know what my formula for it is. And here alpha is a k form. And well, it's a bit hard to draw the formula, but think of a multivector like so. And think of our differential form like so, and then take one index of alpha and hook it up to one index of each. Well, may as well make it the first one. Like so. And then antisymmetrize what's left. So you now have a single multivector from this construction. And that's the answer. Okay? And all other brackets vanish. So just to So somebody can explain, after I make the next statement, where this idea came from. What are the Moret-Cartan elements of this L-infinity algebra? Oops. So these are the vertices of my construction gamma, i.e. the objects of a certain three-groupoid. Okay? And has anybody done the exercise already? They're quasi-Poisson. Is that the word? Quasi-Poisson structures. So they're a pair consisting of a bivector field and a three-form. And the equations that you get, the Moret-Cartan equation is precisely that those two things fit together to form a quasi-Poisson bracket. Whoops, I left out one of the equations. And d omega is 0. Right. So you have a pair of equations because you have the component of the Moret-Cartan equation in here, that's the quasi-Poisson equation, and the component in here, that's the statement that omega is closed. So once you notice this, and this is, of course, how I found this L-infinity algebra, by trying to see what L-infinity algebra would have these guys as its Moret-Cartan elements, then it becomes important to think about the three-groupoid we're getting from this guy. So I've run out of time, but let me just say a few words about this. So this incorporates the action, at least infinitesimally or formally, it incorporates this closed two-form action that we saw in the last talk. In fact, what you can do, the gamma construction is functorial, so you can just map to gamma of differential forms shifted by 2 of m, and this is just the same thing as the Dold-Kahn construction or Eilenberg-MacLane space associated to the shift of the de Rham complex by 3. So the objects here are the closed three forms, and the morphisms are two forms, but the isotropy group of the zero object here are the closed two forms. And this is a fiber bundle. So if you lift one of those one morphisms here up to here, you get the action that we had in the last talk. So so you can explore that at somewhat greater length. I guess that's the point of the talk. Now, here are some questions for the future. The first question is there an extension of the formality theorem to this context? If that can be done, that would be a formal treatment of the theorem from the last talk together with higher data. So it would be saying lots of good things. In particular, it should then include the theorem of Bressler, Gorokovsky, Nest, and Siegen, which is that the formality theorem holds for, or that quantization, formal deformation quantization can be done precisely in closed three-form backgrounds. And their proof is somewhat tricky. It would be nice to see a proof which came through some picture involving this L-infinity algebra. They actually have some L-infinity algebras kicking around which are very reminiscent of this, but not quite as general. The second thing is, how about traces? So as we saw in the last talk, as you perform these morphisms, we have Morita invariance, and therefore the Poisson traces must go over. So there should be a cyclic version of this. In other words, there should be an L-infinite module for this guy, which is constructed out of the differential forms, along the lines of Ziegen's cyclic formality conjecture proved by Scheuchert and Dolgoshev. So I haven't yet, I only thought of this on Wednesday and Tuesday, And I haven't actually been able to find an L-infinite action of this L-infinite algebra on the thing that occurs in Segan's conjecture. But I bet it exists, based on the last lecture. So thank you very much.